Welcome back for some new lectures for Philosophy 201 Introductory Logic. And we've now learned all the proof rules that we'll need for anything whatsoever. So we have the basic foundation for any valid deductive argument. So now let's put that to work in the next couple sessions. So what we're going to do in this session is we're going to talk, where the overarching theme for this session and the next will be, how do we use predicate logic in application, in particular to formalize theories? So now in this case, I'm using the word theory very generally. So a theory is anything where you have a sort of system of knowledge. So in particular, where you have some sort of things that are set down as axioms and you'll argue from those. So the general way we'll set up a theory is we'll have, first of all, a choice of the vocabulary of the theory. So that will mean we'll choose some predicate symbols or names or relation symbols that will be the key concepts in terms of which we formulate things. And then what we'll do is we'll write down some rules that will specifically apply to those symbols. So the first theory we'll deal with today is the most basic theory you can imagine, the theory of pure equality. So we'll introduce a relation symbol, the relation symbol for equality, and introduce some proof rules for that relation symbol. And of course, we'll also talk about the kinds of things we can express using that bare notion of equality. Then we'll go on in the second bit today and we'll talk about the generic idea of a theory of order. So that is anytime you have comparisons, one thing is bigger than another or less than another. And so there are various ways you can formulate a theory of order. So that will be the second order of business today in our discussion. So let's just go straight ahead and start talking about equality. So equality is every relation symbol in logic has an arity. So that is the number of blanks after the relation symbol. Predicates are unary, they have one blank. Then we have relation symbols like X is taller than Y, or X is the mother of Y. Well, equality is also a binary relation like the latter ones I mentioned. That is, it has two places. When you say that something is equal to something, there's two things involved. It is a tradition, who knows why, but people tend to write equality in infix notation. So in other words, in this class, typically we were writing relation symbols. The relation symbol comes first, then the two things after relation symbol. That's prefix notation. Equality, we tend to write between the names or the variables. That's just a convention. It doesn't mean it's a different kind of thing. It's just a convention. I'm going to stick with that convention. Okay, so we all know what it looks like, the equality symbol with the two lines. Now, the only difference is, in this particular case, in general, equality will appear as a component of other things, of other formulas. Okay, so let's start actually just by seeing how much more we can say when we have a notion of equality in place. Okay, the most basic thing we can express with equality is simple sameness relations, right? So we can say something like Clark Kent is, that is of identity, right? So there are two is's in English. There's the is of predication and the is of identity. So if I say Clark Kent is smart, I don't mean he's equal to smart. I mean, he has a property being smart. However, if I say Clark Kent is Superman, depending if you take Superman to be a proper name, which I will in this case, then I'm asserting those two things, Clark Kent, Superman, are identical with each other. Okay, so the way I would formalize that is I would simply choose constant symbols for both of these. So I choose a constant symbol, say C for Clark Kent and S for Superman. I would write CS and simply put an equality sign between the two. Now, again, remember, equality is written in fixed notation. So that is now a sentence, because what it really is the relation equality applied to two names. So now it's a sentence. C equals S. That's a sentence. Okay, so that's the simplest use of equality. Now, what comes as a little bit of a happy surprise is that equality is actually sufficient to express any finite numerical claim. So any finite numerical claim, such as there are less than n or more than n or exactly n, any one of those can be formulated using the logical symbols we have so far and with the addition of the equality symbol. Okay, so on this page, I'll just give you a few examples of that. Okay, let's start with the sentence, there is at most one God. Okay, so here I'm going to take to be a God, in this case, to be a predicate. So it's a property that something can have, being a God. So I'll just introduce a predicate symbol, G, and I want to say there is at most. Now notice that's very different than what we said so far with our quantifier. So the existential quantifier, you can say there is one or more. The universal quantifier, you can say there is every, but how do you say there is at most? It doesn't say that any exists. It says there's no more than one. So there may be zero, there may be one, but there's no more than one. So that's the question. How do we formalize that? Well, the key is now to use equality together with universal quantifier. So what we're going to say is if you take two things, now remember when we have two quantifiers, like for all x, for all y, we're not committed to there being actually two. So the fact that x is a different symbol than y doesn't mean that x is different than y. Okay, it is, I've used before this analogy, it's like you have a barrel full of balls and you draw a ball out of the barrel, but as soon as you draw it out, you put it back in. So if you say for all x, for all y, you pull out one and say x, and you say something about it, then you put it back in and you pull out another and say, and y. Okay, so this doesn't commit us to saying there's two. In fact, the sentence I'm going to write now says there's at most one. So here's how we do it. For all x, for all y, if both x and y are gods, then they're the same. So that's x equals y. That tells us actually x and y aren't different. They are in fact the same. So this says take two things. If the first is G and you put it back in the barrel, you pull something out again. If it's G2, it's the same as the first. So in other words, there's at most one. That's the best. That's as many times you draw out. If it's a God, it's always going to be the same thing. There's at most one God. Okay. So now let's go in the opposite direction. So now we want to say there are at least two gods. So let's think about that now. So the existential quantifier exists x, says there's some. That doesn't tell you anything specific. There's one, there's two, there's 10 zillion. It doesn't matter. Now we said there's at least two. So we just need to rule out the case of one. And here's how we'll do it. We'll now use the existential quantifier. We'll say there is an x, there is a y. Still, that so far this doesn't express two. It just says there is. That could just be stuttering so far. But now we want to say such that the first is G, a God, and the second is a God, and then finally, it is not true that those two are equal. Okay, so this says x is a God, y is a God, and x is not equal to y. So that rules out the case they're the same. So there's at least two. There may be three, there may be more, but there's at least two. Now, in general, in the future, it's very convenient. This sign here, the symbol, not x equals y. Sometimes we'll just put x. You've seen this before, of course, with a equals and then a strike across it, just a very convenient notation. So sometimes we'll write that instead of not x equals y. Okay, so let's just do a couple more examples on this page. Then next thing we'll do is learn how to do proofs with equality. So now we want to say here, the next one, number 4, Alice respects nobody but Bob. Okay, so there's actually, in this sentence, there are actually two things going on. So this does, insofar as I'm a competent speaker of English, this implies that Alice respects Bob. So it doesn't say Alice respects maybe Bob, but nobody else. It says Alice respects Bob and nobody else. Okay, so let's think how we can say those two things. So we want to say, first of all, just that Alice respects Bob. So now I'll introduce a relation symbol for that, R. Alice respects Bob. That's it. But now we want to say Alice respects nobody but Bob. So now we want to say, and for anyone that Alice respects, that person is Bob. Okay, so Alice respects Bob, and by the way, anyone who Alice respects is Bob. So there's no one else besides Bob that Alice respects. Okay, it turns out what I just wrote, there is actually another way to write it, a kind of cool, compact way to write that, is it's equivalent, what I just wrote is equivalent to, for all x, Alice respects x, if and only if x equals Bob. So that's actually equivalent to the thing I wrote before. Okay, so those are a few examples of the things we can say with equality. The last one on this page, number 5, is, let me just put it this way, it's a little bit philosophically controversial. Now this is a class in the philosophy department, but we have something important we need to do, and that is learn how to do logic. So I'm only going to take a brief moment to talk about the philosophical issues. It's something you can discuss in precept. So the next phrase, the P is Q. The definite article the in English is a funny thing, right? Because when you say the P, if you say there is a P that is Q, that's one thing. But if you say the P is Q, that has a much stronger oomph to it than just saying there is something that's both P and Q. So there is some controversy about what exactly that means when we say the P. Now, there's a classic analysis of this. And in fact, this was one of the first moments in the history of formal logic and philosophy, where a famous philosopher, Bertrand Russell, said, we finally can understand what that expression means, the P is Q, if we use quantifiers and equality. So Russell said the right way to think of this phrase, the P is Q, is it's actually a conjunction of two things. It says, first of all, there is a unique P, and it is Q. So that's really what we're going to try to express here. Is the most important part is, how do we say there is a unique P? So how do we say there is a unique P? Okay, well, that again is itself is a two-part thing. There is one, and it's unique. There is no other. So it says there is a P and it's the only one. So I'll write that like this. There is P and anything that is P is equal to that original thing that you wrote down. Okay, so that is, there is a unique P. What I just wrote there. Now we can easily take what I just wrote there and turn it into the P is Q, because then we just say there is a unique P and that thing is Q. So I can just add a new conjunction onto the end. Still under the quantifier exists X, QX. Okay, I won't write that down here, just so we can keep this up on the page here. There's unique P is formulated this way. If you want to say the P is Q, you say there's unique P and it's Q. Okay, so that's just a very, very small taste of what we can express using equality. Now, in a second, we'll come back and I'll give you a couple of other examples, but let's now talk about proofs with equality. Okay, so in general, as I said before, when you introduce a theory in predicate logic, you do two things. You introduce vocabulary that you want to use, and you introduce rules that apply to that vocabulary. Equality, there's various rules you might think must hold for equality. People thought about this, and the two most elegant rules to assert for equality that will give us everything we need. The first one is equality introduction. And that says simply, you may assert for anything that is equal to itself. So on the page in front of you, if you look on the left-hand side there, equals intro. So on an arbitrary line, here I've just called it N, that's any line in any proof, you may write for any name whatsoever. So like A equals A, and just say equals intro. Now, obviously that should be valid, right? Just saying everything's equal to itself. Even if you think there's some things that humans just can't doubt, this is one of them, right? A equals A. That's equality intro. Now you might think that should never be useful. Why would you need to say that? But we'll see in a minute. It is actually quite useful to be able to say that. The second rule for equality is equality elimination, and that's a bit more tricky. In fact, the equality elimination rule is what you might call a schematic rule. So if you look at the thing on the right here, it says, given on line M that you have A equals B. That could be that's schematic already in the sense that A and B can be any names you want. But this rule is even more schematic in the sense that on line N here, phi is any formula you can imagine. So it doesn't have to have any particular form. It's any formula as long as the name A occurs somewhere in the formula. Okay, so if you have any formula, as we have here on line N, with A in it, then the rule equality elimination permits you on a subsequent line, here I've called it O, to assert phi, that formula you had on line N with A in it, take A out, put B in. So this says replacing equivalent things. So if A equals B, you can replace the name A with the name B. That's equality elimination. So you're not really eliminating equality. What you're doing, a more suggestive name for this rule would be replacement with identicals, right? So you can replace an identical. If you know it's identical from line M, A and B are identical. You know on line N that something is true of A, then you may assert on line O that same thing is true of B. Okay, cite MN equality elimination. So we believe that these two rules, equality intro and equality elim, you can prove anything that the concept of equality actually that is true of it. So in fact, you'll see equality intro is the same thing as saying that equality is a reflexive relation. Everything bears that relation to itself. We can now prove using these two, equality intro and equality elim, that equality is symmetric. So in other words, so this is one of the wonderful things about logic is these rules you've always taken for granted. And if you're very philosophical, occasionally you might think, why am I permitted to do this? What are the rules? So something you've probably never taken for granted in your life is that you can flip equality signs. So if you have A equals B, you have B equals A. You might thought, wow, but the truth is, whoever told you you could do that? So one nice thing about what we have here is we have a clear sense of what is given and what's provable. What's given is equality intro and equality elim. Symmetry of equality, A equals B implies B equals A, is derivable from those. So let me just prove it really quickly for you. So down here, we're going to take as our assumption A equals B. And we're going to prove B equals A. Now, the way we'll do this is we'll actually, first of all, use equality intro. So notice equality intro, we need to add no new dependencies. So we need no dependencies besides 2. So this is just equality intro. Okay, now the thing to notice here is the formula. So let me use a different color so this is very clear to you. So this formula here on line 2 is an instance of phi A. But in this case, where the A is on the left-hand side. So this is phi A, where we're thinking of the A in phi A is over here. So in other words, phi X is the formula A equals X. Oops, sorry, that's just the opposite of what I meant to say. Phi X is X equals A. Okay, X equals A. Okay, so now equality, look on line 1, we have A equals B. That's exactly like the equality elim, set up for the equality elim rule. We have A equals B on line 1. On line 2, we have a case of a formula with an A. So on line 3 now, we can replace that A with B on line 2. So that's 1, 2 equality elimination. So there we've proven now that equality signs can be flipped using those two rules. Okay. Now, in general, with these two rules, sure, practicing, you'll get more confident using them after you practice, but these aren't tricky rules. But I'll go ahead and give you an example here of a proof using equality intro and elim. And it's a proof that's actually, the fact here is somewhat interesting. So we're going to see here that the claim that A is F And everything, so you'll remember I told you earlier, I said, you can express, I gave you an example. I said you could express compactly the idea that, for example, this is the only one of a certain kind, this thing A, there's two ways you can express it. I'm going to prove that here. So here we're going to say that this is going to be A is the only F. That's sort of what we're trying to express here. A is the only F. There's two ways we can express that. The first way is to say A is F and anything that's F is equal to A. That's the thing on the left-hand side. On the right-hand side, we have something is F if and only if it is A. Now, intuitively, those should be equivalent. So let's prove this one direction of this equivalence. Okay, and before we get going, let's do a little bit of strategizing. Okay, if you look there at what's on the right, you'll see that under the quantifier, under those parentheses, it's a biconditional. Now, if you look on the left, you already have one half of it, right? If you ignore the for all x quantifier, if you look on the left, you already have fx arrow x equals a. So that's going to be okay. What we're going to want to get to finish the proof is we're going to want to get the other direction. We're going to want to get if x equals a, then fx. Okay, but we want to get that's true for anything. So in essence, what we want to get is for all x, if x equals a, then fx. Okay. So what I'm going to do is I'm going to assume, very first of all, I'm going to take off this FA here from line 1. Okay, now I'm going to assume on line 3 that B equals A. Why am I doing that? Okay, here's the thinking. So I want to prove a universal sentence. I want to prove f of x if and only if x equals a. A good strategy sometimes for that is pick an arbitrary thing, say b, show that fb if and only if b equals a. That's what I'm going to do. So I've chosen b. I just have it in the back of my head. It's an arbitrary name. Who knows what it is? I'm going to assume b equals a and try to prove fb. Now, this is not going to be a problem because actually, in this case, I have FA here on line 2, so I'm just going to do an equality elimination. I'm going to be super nitpicky for a second here because line 3 is not the right form for equality elimination. Actually, it's A equals B that I need. So I'm going to just allow myself to substitute in the proof I did on the previous page of the symmetry of equality. So I'm going to do this. I'm going to make a little note. Hey, I did that on the previous page. Okay, so that's just an instance of cutting in a proof I've already done. So that depends on 3. And now I can assert FB. So that's from 2 and 4 equality elimination. Okay, and so therefore I have if B equals A, then FB. So that's 3, 5, conditional proof. Okay, and now I'll take off from line 1. I'll take off that other side for all x. If f of x, then x equals a. And I can take the instance of that with b. So I'll have now if fb, then b equals a. Okay, so now lines 6 and 8 are the two halves that I need to put together to get this biconditional that's going to give me the result I want. So I'm going to now conjoin the two, do biconditional introduction, generalize. So that's how we're going to finish this proof. So I'll start by putting these two together. So we have if FB, then B equals A. And if B equals A, then FB. So we have 8, 6, and introduction, both just depending on one. Okay, now biconditional introduction, FB, if and only if B equals A. And so now that line 10 depends only on one. The name B, now notice in line 1, the name A occurs, but I'm not going to generalize on A, I'm going to generalize on B, and B does not occur in line 1. So now I'm permitted to use universal introduction to say for all x, f of x, if and only if x equals A. So that's 10, universal introduction. Okay, so there you see, we had to use our equality elimination back on line 5, but that enabled us to show the right-hand side here. Something is f if and only if it equals to A, it's equal to A, follows from the left-hand side. Okay, so the last bit we're going to do with equality is we're going to take another quick glance at the expressive power of equality. So what can we say with the equal symbol? Now, as a quick preview, I'll tell you, as I mentioned before, any finite numerical statement can be expressed with equality. So things like there are at least n such and suches, or there are at most n so-and-sos, or there are exactly n something or others. Those all can be expressed with equality. I'll sketch for you here how that can be done. Interestingly, actually deeply interestingly, but it's not something we're going to talk about today, you can't express claims about infinity using just the equality symbol and the quantifiers. You can't say there are infinitely many. That's just impossible, and it's known that it's impossible. That's a philosophical issue that comes up in this setting. So let's think about how we express there are at least n. We already saw how to express there are at least 2. How did we do that? We took 2 existential quantifiers. We remembered just because there are 2 quantifiers doesn't mean there are 2 things. So throw in some non-equals symbols. Okay, it's easy for 2 because you just say there's an x, there's a y, x doesn't equal y. It's a little more tricky as soon as you get to 3, but you just have to make sure that you say all the things are not equal to each other. So for example, if you want to say there are at least 3, you have to put in 3 existential quantifiers, exist x, exist y, exist z. And then you need to make sure that none of the pairs are equal. So you need actually x doesn't equal y, x doesn't equal z, and y doesn't equal z. And I'm just going to put ... because I don't know yet. Am I just going to say there are at least 3 things, in which case I would be done with this formula? Or do I want to say there are at least 3 things that are p, in which case I'd say x is p, y is p, z is p. Okay, but in any case, that's the key to expressing at least, is you use existential quantifiers, and then for all the things you say exist, make sure to say they're not equal to each other, and that assures you there are that many things. Okay, there are at most is also the same kind of thing. So remember, if we want to say there's at most 1, what you have to do, so with at most, you have to go up a number. So here's what we're going to do, is if you want to say there are at most n, you actually have to say for all n plus 1, one thing is going to be equal to one of the previous n. Okay, so it's a sort of a pigeonhole thing where you're saying if you have n pigeonholes, then if you take n plus 1 things, 2 things are going to fall in the same hole, so to speak. Okay, so to say there's at most 1, you say for all x, for all y, x equals y. That makes the 2 things have to go into the same pigeonhole. If you want to say there are at most 2, we'll use 3 quantifiers. So we say for all x, for all y, for all z, 2 of them have to be equal to each other. So either x is equal to y, or x is equal to z, or y is equal to z, ... Because we don't know yet. Again, do we want to say just there are at most n things, at most 3 things, or do we want to say there are at most 3 p's, in which case we say for any x, y, z, if they're all p, then 2 of them have to be equal in this case. Okay, good. So that's how the generic form of there at least n, there at most n. Now, it's of course easy to see that if you want to say they're exactly n, you can just conjoin the 2, right? You can say they're at least n and they're at most n. So if you want to say they're exactly 2, they're at least 2 and they're at most 2. Just conjoin them. But there's a cool way actually to say it more directly. And that is, you can just say, if you want to say there's exactly n, you can say there exists n distinct. And if you take anything, it equals one of those. So let's just do the case of 2. I'll write down the case of 2, and then you can probably generalize from that. Okay, so I want to say there's exactly 2 things of a certain sort. What I'll do is I'll say there is an x, there is a y, x doesn't equal y. Now, so far it just says there's at least 2. There may be more, so we want to rule out the more. So I'll say and for all z, either z equals x or z equals y. Again, with dots, because I wouldn't need the dots. I could just stop the formula now if I want to say there are exactly 2 things. That would be a complete formula. Say there is an x and a y. They're not equal. For any z, z is equal to x or z is equal to y. That would say they're exactly 2 things. If I want to say they're exactly 2 p's, I would say there is an x, there isn't a y, there is a y, x doesn't equal y. X and y are both p. And for anything that's a p, it's equal to one of those 2. Okay, so that's the generic form of the equality statements. So that's the theory of equality. The truth is it sits in the sort of background of most of the things we do. So in fact, some logicians have said it actually should be considered, equality should be considered like conjunction, disjunction, like part of logic itself, not part of a theory on top of logic. Well, we don't need to go into that issue here. But we know now explicitly how to formulate that background theory of equality that gets used in almost every other theory that we use. So it's sort of the starting point of all subsequent theories. Okay, so as promised, the other thing we're going to do now is we're going to talk very briefly about order relations, the concept of an order relation in general. So to formulate a theory of an order relation, what you need is a single binary predicate symbol. Okay, so you need a symbol like RXY. So you can say X is related to Y in this way. They're ordered in some sense. Now, for some reason or other, historically, we have tended in mathematics, we tend to use, instead of RXY, we tend to use these good old fashioned, you remember the alligator symbol, right? Less than and greater than. We tend to use these symbols. And we, of course, have an option. We can use strictly greater than, strictly less than, or greater than or equal. Okay. It turns out to be convenient for our purposes to use something that's like greater than or equal. Okay. That will allow me to sort of give you a set of basic axioms that's nice and elegant here in a minute. But let me just remind you that we cannot, the key to logic, or a key idea in formal logic, is nothing is left to intuition. So you can't assume that the less than or equal sign, it's just a symbol, right? It's like R, so it doesn't come with meaning. Any meaning it has, we have to give it by axioms. So if you look down here at the generic concept of an order relation, I've written down a set of axioms that we do assume, normally when we write the less than or equal sign, we assume it has these features, but let's just stipulate that explicitly. So the first feature is less than or equal is transitive. If x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. Okay, so one thing is less than or equal to second, second is less than or equal to third, then the first is less than or equal to the third. We're making that an axiom. Okay, the second axiom we'll put in is that our order relation, less than or equal, is reflexive. Everything is less than or equal to itself. Okay. And the final property we put in for this order relation is it's anti-symmetric. Okay, so what that says is if you take two things and they're both less than or equal to each other, that must be because they're equal. So if x is less than or equal to y and y is less than or equal to x, then x equals y. Okay, now these three axioms are fairly weak in the sense that they're compatible with lots of different kinds of order relations. Okay, so I'll just give you a couple examples here. The goal for this little bit right now will be to start to help you develop an intuition about how you would capture specific features of order relations by adding new axioms, new statements that would be true in those settings. Okay, so if you look at the first example on the left, what I've done here is I've put arrows. So I have this first example, there's four things, A, B, C, D. Now you should, when you stare at this little diagram, don't think of A, B, C, D as symbols. Right now, think of those as actual names of things. So it's like, these are things, A, B, C, D. And they're ordered in the following way. A is at the top, then B and C are below, and D is at the very bottom below everything. So D is below B, B is below A, D is below C, C is below A. We're assuming transitivity, therefore D is below A. Everything is, less than or equal to itself. So that's an order relation. It happens not to be what we call a total order because B and C here are incomparable. That is, B is not less than or equal to C. C is not less than or equal to B. We actually don't know directly how to compare them. It's not as if we're saying they're on the same level. They just, the relation doesn't say anything about the comparison between the two. So that satisfies the axioms, transitive, reflexive, anti-symmetric, if you understand it in the way I just described. It's an ordering. If you look now at the middle example, it's like that. We've lost one of the elements, but now I've forced these into a strict ordering where A is at the top, then B, then C. This is a, naturally enough, you might want to call it a linear order, right? Everything sits on a line. Now, the way we could capture that with an axiom, we could say we want to rule out the kind of thing on the left there and focus only on the kind of thing in the middle there, is we would say any two things have to be in the relation with each other. So any two things, I'll write that down here. So a linear order, it's going to tell you that for any two things, any X, any Y, either the first is less than or equal to the second, or the second is less than or equal to the first. Okay, and that applies, as just mentioned, that applies not to the thing on the left, but it does apply to the thing here in the middle. So that's a linear order. Okay, however, we do know, of course, there are different kinds of linear orders. This one in the middle is a pretty boring linear order. It's got three elements. It has endpoints, right? So A is at the very top, C is at the very bottom. It doesn't go on infinitely in both directions. We know lots of interesting examples of linear orders that have much more interesting structure. So one such example that I haven't written down here is the natural numbers, the whole numbers, right? 0, 1, 2, 3. They're ordered, right? 0 is less than 1, 1 is less than 2, but it goes on forever. So there's no top point in the natural numbers. And you could write an axiom that said that, right? You could say, and this, take this as a little exercise for reflection. How would I say that for any number, there's always a greater one? So you could write down an axiom that says for any number, there's always a greater one. Okay. Then the last example on this page, if you look on the right here, is I've written the symbol Q, and Q is the symbol that mathematicians use for the fractions. So rational numbers. So these are numbers that can be expressed in the form A over B, a fraction. Now, the fractions, like the natural numbers, form a linear order that's unbounded, and it's actually, in this case, unbounded in both directions. You have infinitely, you can go back negative as far as you want, you can go up positive as far as you want, but there's also something more interesting here with the rational numbers, and that is the rational numbers are a dense order, okay? a dense order in the sense that if you take any two fractions, no matter how close they are, you can always find yet another one between the two. So it's totally dense. That's really quite counterintuitive if you think about it for a minute, because if you take two, there's always one between those two. But if you take that one that's between and one of those two, there's yet another one between. So it just goes on forever. You take anything, any two numbers, any two fractions, there's infinitely many things between them. Okay, that's the property. And we can write down an axiom for that as well. I'll indicate very quickly what such an axiom would look like. It would be something like this, right? We'd say, if you take for any x and for any y, if, for example, so in this case, we know that one of the two is less than the other, but let's suppose that x is less than or equal to y, then what's going to happen is it's going to follow that there is something. So in this case, to express it properly, we'd have to be a little sophisticated. What we want to say is, if x is less than or equal to y and they're not equal, so I'm going to go back and add that as a condition here. So if x is less than or equal to y and x doesn't equal y, so that's really just saying x is strictly less than y, there's going to be something that's greater than x, less than y, not equal to either one. So that's going to assert the existence of a something between the two. Okay, so I'll quickly sketch that for you. So say z, and I'm going to allow myself to abbreviate less than equal or less than, use less than as an abbreviation for less than or equal, but not equal. So there's a z such that x is less than z and z is less than y. Okay, so for any two things, if they're not equal, one is less than the other, there's something strictly between the two. That's true of the thing on the right, the fractions. It's not true of the natural numbers. It's also not true of the thing in the middle in our picture here, and it's not true of the thing on the left. Now, there's lots of different properties one could ascribe to orders. There's lots of different types of partial orders, these order relations. And they come up a lot in various sciences, in mathematics and physics and economics and so on. However, the good news is proving things about orders and order relations, there's no new knowledge needed. All that's required is you set down the axioms that you need for the description you want to give, but then the proofs will always proceed just by the rules we've already learned. Okay, so rules like universal quantifier elimination, introduction, etc. Okay, so today we talked about these two particular theories, the theory of equality, which will sort of line the background of almost every theory, and then theories of order, where we can describe a constellation of things that have some kind of order with each other. So that will be it for this session.